for NEET is now available on the Google Play Store. Try it out for free.
Good morning, everyone. Good morning, everyone. I know it's very early, 7:30 a.m. in India, and we are planning to move this lecture a little bit later to the day. Um, but for now, it is here for whatever reason. You know, early rise. Brahma Muhurt. So, but it's good to have these lectures early in the morning because they lend you a chance to schedule your other lectures later, you know. So that is a huge plus. Okay. So today I'm going to continue the discussion with solving problems for with respect to angular momentum, torque, and rotation. Okay. Now rotation is not easy. you know there are many different ideas that come under the auspices of rotation, as I explained last time. So let me get going now, and I will quickly review everything, and then we'll go from there. Okay. So here is the story. The So when you have work is the dot product of force and the distance over which that force is applied, right? F dot ds over a path integral defines work. Okay, this is a very important definition that we discussed, right? Then we discussed angular velocity, and we said angular velocity is a vector just like linear velocity, right? So in rotation, when something is spinning like this, we say that the direction of the angular velocity is upward. So if it's spinning like this, the direction of the angular velocity is upward. So in this case, you see, the direction of when something is rotating from p to p time the xy plane, the direction of omega is z, is along z, right? So let's say it goes from p to p prime, it's along the positive z direction. Okay, so when a top is spinning like that, the vector is that way. Right now, if the top is spinning like this, then it is this downwards. Okay, so that's what you need to look at. Okay, so the instantaneous angular velocity is given by d theta by dt, and its direction is given by the right hand screw rule. Okay, by curling your hand. Right now, what is the direction of the velocity of a particle or a point on the top, right? Let's say every point on the top is rotating, right? Now every point has a velocity. Now that velocity, what is its relationship to the omega, right? Omega is, if it is rotating like this, omega is upwards, right? So now a point there, like, right, what is its velocity? It is omega. Omega is upwards, right? Cross r, right? So that point is, like, for instance, you see here, right? The r1 is that way, it is rotating like this. So omega cross r is v. Okay, so that is the direction of the velocity. The velocity is always like that, right? The velocity is tangential to the to the path taken, right? Velocity is always tangential to the path taken, regardless of the curve. You have a something going in an ellipse, the velocity is always tangential to the ellipse, right? So now, so how do we calculate it when we have omega and r? Is omega cross r. I already explained this. V equals r omega, v equals r omega, v equals r omega, but v is a vector, omega is a vector, r is a vector, omega cross r. Okay, so then we introduce this case when something's going faster and faster and faster. We said alpha cross r, right? Alpha cross r is the Tangential acceleration. Something is going in a circle, right? Its velocity is changing, right? If it is going in uniform circular motion, its velocity is changing. Its velocity is changing not in magnitude but in direction. And therefore, if you see v1 minus v2, right, that will give you delta v, right? So delta v by delta t, right? Delta v by delta t will actually be radial in the same direction as r. Okay. So now when it goes faster, faster, and faster, and faster, there will be two components. There will be both a radial component and a tangential component. Therefore, the net A will be a combination of AT and AR. Notice that AT and AR are always perpendicular to each other. AT is always tangential. AR is always radial. Therefore, they are always perpendicular to each other. So you have two vectors which are always added, which are always perpendicular, and therefore you have an AT and an AR. So instead of doing something in, what is that, Cartesian coordinates, you will do some of these things in polar coordinates, or in three-dimensional r dr d theta type of coordinates. Okay, so you must learn that kind of calculus as well, r dr d phi, r dr d theta, like that. Okay, r d phi d theta. Okay, so there they have two angles. Okay, so you must understand how those angles play out. Okay, so so polar in three dimensions, little bit's worth learning. Okay, you may not see it in your JE or your NEET, definitely not in NEET. Okay, but in JE you may see occasionally. But main thing is you must understand this, that here the AT and AR are always perpendicular to each other, and they are therefore componentizable. One AT comes as a result of torque. I already discussed torque last time and we looked at all these things. The other comes as a result of uniform circular motion, right? So a the sun, earth going around the sun, if you said it is going in a circular motion, right, then it is actually going in a elliptical orbit, right? The direction of the orbit, right, is always, right, the direction of the force is always radial only. The direction of the force is always radial only. Okay, so because it is only radial, what can be said? That the acceleration is also only radial because of F equals ma. Okay, now when something goes faster and faster and faster and faster and faster, there is another force, right? And actually that force comes as a result of, it's not one force but actually two. It is a result of, or a turning force. It's a screwing force, and that produces an angular acceleration, alpha cross r. Okay, that is called AT, tangential acceleration. Okay, so AT is alpha cross r. You have the tangential acceleration and you have a radial acceleration. Okay, so now when something has both a radial and a tangential acceleration, right? So using that, then you take the derivatives. Okay, these derivatives is what they are discussing in this slide. Motion of a particle in two dimensions. Okay, when you discuss motion of a particle in two dimensions, you have to include its motion with respect to the radial and tangential. Okay, so AR is R times ER, its derivative is dr by dt ER plus R times dE by dt. Therefore, you have these two parts to the velocity. Okay, one is the tangential and the other is the radial. Now, in uniform circular motion, there is only that tangential component. Okay, so now, so when a particle is moving in 2D, right, if it's moving in a perfect circle, there is only that radial component. Okay, the velocity, or there's only the tangential component for the velocity. Okay, the acceleration is only radial for uniform circular motion. Now, if you break up that acceleration into both, the acceleration is always only tangential. The velocity is always only tangential. Let me rephrase it. I don't want to confuse everybody. The velocity is always only tangential. Okay. The acceleration, on the other hand, is can be both tangential and radial. Now, for a particle which um, for a particle which moves in a circle, right? The what happens is, the for a particle which moves in a circle, the acceleration is both tangential and radial. Okay, so then what you have is the the tangential acceleration is related to how much faster and faster something goes. Okay, while the radial acceleration is related to the uniform circular motion part, side of it. Okay, so and that's how this all works. Okay, so so you have two components. There is a, which is equal to v square by ar, which is equal to v square by r. Okay, that is omega cross v. We said v equals omega cross r, and ar equals omega cross v. And then we have at, which is alpha cross r. Okay, so at is alpha cross r. Okay, so these are the two components. You have the tangential component, the radial component. Why did I belabor this? So that you understand the two parts. This is a central idea in rotation. Okay, now everything else we learn is premised on your full understanding of this. Uniform circular motion, there's only a radial acceleration and there's only a radial force. Okay, so this is a very critical idea. Okay, so now we are going to discuss next this idea of what causes this faster and faster kind of motion, which is what causes alpha. Alpha is angular acceleration. In uniform circular motion, what is the angular acceleration? Zero. Things are not going faster and faster. They go at a fixed speed. Okay, so now So now you have, we will discuss this idea of torque, okay, and angular momentum. Okay. Now these quantities are related. Torque and angular momentum are related, just like um, um, momentum and force are related. What do I mean by that? Okay. How are momentum and force related? Right? Momentum and force are directly linked. One is the derivative of the other. dp by dt equals f. Right? So similarly, d angular momentum is L. dl by dt is tau, and tau is torque. Okay. So the rate of change of angular momentum is the torque. Rate of change of momentum is force. Okay, torque is also a vector. Okay, so now what you need to understand is that under certain circumstances, something which rotates like that, right? It's rotating and also its axis is rotating. Okay, that is that top. When you give a top a tap, it will rotate like that, right? Why does it do that? That it does that because there is a torque that comes into play. Okay, and the direction of the torque, right, the rate of change of that, the angular momentum is continuously changing. In what way is the angular momentum changing? Changing only in direction. Just like in uniform circular motion, the acceleration is continuously changing, right? Changing in what way? Only in direction, right? So when, let's say, something is going uniform circular motion under the force of gravity, right? Or there is a nucleus which is positively charged, and there are electrons which are negatively charged. We say they go around in a circular orbit or an elliptical orbit, right? So when that happens, right, what you have is you have the rate of change of velocity, right? And so that force, rate of change of velocity, is the acceleration, right? Rate of and how does the acceleration how does the velocity change only in direction, right? Similarly, when something is revolving, when the angular momentum is revolving like that, right, it is changing only in direction. The top is still spinning at the same rate. What is angular momentum? What is linear momentum? Linear momentum is mass times the velocity. Like that, angular momentum is a constant called the moment of inertia, which we will discuss next, times the angular velocity. I omega is L. L equals I omega dl by dt is tau. Okay, so that is the relationship between torque and angular momentum. Why did I do this? So that you understand this. We already discussed these equations. V equals omega cross r, at equals alpha cross r, ar equals omega cross r, or omega cross v, right? We already discussed these equations. Now, what is torque? Torque is the moment of a force, right? So when do you typically have torque? You have torque when you have this kind of uh, turning moment. Okay, so if you have two forces which kind of act and cause uh, turning or rotation, then you have torque. Torque is r cross f. It is the moment of a force. Moment of anything is r cross that something. So angular momentum is the moment of the linear momentum, r cross mv. So torque is r cross f. Okay, now what does this added moment of something introduce? It introduces this idea of rotation. Okay, so r cross f is moment of a force, r cross mv is moment of momentum. Moment of momentum is the angular momentum. And just like the rate of change of linear momentum is the force, the rate of change of angular momentum is the torque. Okay, so tau is equal to the rate of change of angular momentum. So how do you calculate r cross f? You put ijk, and in this case, is a very simple thing. He has, he has a point about which he's calculating. There is this point. This is experiencing mg. There is this mass which is of weight m, which is experiencing mg. So what is its torque about this point? Its torque about this point is r cross mg. And let's say it came, you had, it had come down here, then it's what is that? Its torque about that point is also still r cross mg. Okay, the r changes, but the angle also changes. Therefore, you end up with the actually the same torque, right? So the torque stays constant. Okay, therefore he ends up with mg times k, right? So um why do you end up with that? Okay, and mg times k is what? In that direction. So the torque is the cross product, right? So if you had a force in the xy plane and r in that same xy plane, the torque will be in the z plane. That's how he ends up with x mg x times, and the direction is along k, right? So in this case, r cross mg will be in that direction. Okay, so you use your right hand in calculating. So you go from r to g, r cross mg. Therefore, it goes into the plane. Okay, so x, y, and z. Okay, so And how do you evaluate the R cross F? You do ijk x minus y 0 0 mg 0. Okay, so then what is the angular momentum? The angular momentum is L equals R cross P. Okay, and that is RP sine theta. Okay, that is the angular momentum. Okay, so now the relationship between torque and angular momentum is what? Right? The relationship between torque and angular momentum is rate of change of angular momentum is the torque. So when you calculate the rate of change of angular momentum, L equals R cross P, dr by dt cross P. What is dr by dt? Dr by dt is V cross P is 0, right? Plus R cross dP by dt, right? R cross dP by dt will produce you R cross F, right? The first term goes to 0 because P is just mv and dr by dt is V. So V cross V is 0. Therefore, you will just end up with dl by dt is R cross dP by dt and R cross dP by dt is F, right? So therefore, dl by dt equals tau. And what is L? L is the angular momentum. Momentum of the moment of the momentum. So this is a very important equation. Dl by dt equals tau external. So external forces cause torque. So dl by dt equals tau ext. Okay, the analog to that equation dp by dt equals fext. Okay, so you have equivalents in rotation, and you also have, okay, so that's how you have to figure this out. Okay, so so fext equals 0, dp by dt equals 0, and therefore you had, when the external there's no external force, you have conservation of momentum, right? Similarly, you have, when there is no external torque, there is conservation of angular momentum. Now, when a planet is going around the sun, right? Then uh, uh, when a planet is going around the sun, right? What happens, right? The planet is going around the sun. You have only a radial force, right? And therefore, above that about that axis, there is no torque. Okay, you only have uniform circular motion. There is no torque. Because there is no torque, you end up with conservation of angular momentum. Because there is no torque, there is force. There is one force which is only radial. When there is only a radial force, there is no torque. Okay, your R cross F, R and F are in the same direction. Because R and F are in the same direction, there is no torque. Okay, R cross F. So there is no torque, and as because there is no torque, L is conserved in, planet goes around the sun. Okay. So that is, those are all the main ideas that you have to understand. Okay, now you've once we've gone through this set of ideas, then we go on to the next set of relations. Okay, the next set of relations deal with calculating moments. Okay, so now why do we calculate this moments? Okay, now, when you have a rigid body like a ladder which is kept in against a wall, right? You end up with these questions where you have to use, or there are struts in a building, right? You do a lot of these questions in engineering mechanics, and so in all these cases, you have to take, in addition to a force equation, you also have to take moments. Okay, so about an axis you will take moments, and you have to choose the right axis about which you take moments. Okay, so in the dynamics of a lever, in the dynamics of the ladder, all these ladder problems and these lever problems, they all deal with the dynamics of a rigid body. And sometimes when we say dynamics, the body may be stationary. So you evaluate moments and the moments will be zero. Okay, so that is very important thing, point to learn, right? When you have a body at rest in statics, you say the net force is zero. Like that, if the net torque is zero, then it will not rotate also. The body is at rest, it doesn't rotate also, right? So then you can also, you get an equation that you get from moments. Okay, so translational equilibrium dp by dt equals 0, sigma fi equals 0, f external is 0, right? Rotational equilibrium, you get dl by dt equals 0, therefore tau I equals 0 and tau ext equals 0. So in this case, we have f and minus f. Therefore, when you take moment of the couple, you have r1 times minus f plus r2 times f. Therefore, the net moment of the couple is r1 minus r2 times f. So, in the case of a couple, which, what is a couple? A couple is two forces having equal and opposite directions. So now when you have two forces which have equal and opposite directions, they tend to produce a rotational motion, right? But what is the moment of that couple? It is independent of the axis about which you calculate the, so regardless of your r1 and regardless of your o, right, you end up with the same moment. Okay, what is moment? Moment is the torque by the couple. Okay, so in this case, r1 minus r2 is just ab, right? You know from vectors, right? R1 is this, R2 is this, R1 minus R2 is just AB. And regardless of where your O is, R1 minus R2 will always be AB. And therefore, when you R1 minus R2 times F will give you, so when you have equal and opposite forces, right, which cause a torque, right? So in this case, when will these are not equal and opposite with respect to a some kind of force equal, like a force pair between A and B, where A is applying a force on B, B is applying force. These are not like that. These are, these involve, let's say there are two bodies being attracted by a third body, right? And but then they would then in that case they will all have different forces. But if two bodies, they have this kind of torque producing action. Okay, and so one kind of couple is like when you have a molecule, right? You have a O and two H's, right? H2O, right, in water, right? So there is a potential for a torque there, right? So in such cases, you end up with two forces which are equal and opposite, okay, and therefore they have a torque. Okay? So you have to understand that now. So that is a, what is called a couple. Okay, now I'm going to go on to discussing lever, which is a little bit different from what we just now discussed, which is the moment. Okay, so now in a lever, what is a lever? Okay, a lever is, you have a point and then you have a body which rests on that point. Okay, an ideal lever will have very little mass, but there will be forces that are applied on either side. A lever with mass also, you can still do the same problems. Okay, so now here is the lever. Okay, now like a seesaw, think of a seesaw, and there are two children sitting at A and B. The only point is that the seesaw has one of one length and the other of another length. Okay, this is D1, this is D2. Now there are two kids sitting here. Now the point is that if the two torques are equal, then the seesaw will stay steady. Okay, so if you put a little boy here and a big boy, or the other way, if you put a big boy here and a little boy there, right, the little boy will end up with, because the distances are proportionately different, the little boy may actually be able to balance out the big boy because the lengths are different. Okay, so O is the point of the fulcrum. If the weight of the little boy is here is F2 times D2 equals F1 times D1, then about this fulcrum you will have zero torque, and the the mechanical, and therefore you have the ratio D2 by D1 is said to be the mechanical advantage, because you can change the force that you're applying. So when you have a lever, right, when we dig using, I'm sure you have seen that they will push it and then they will push it down, right? So the force that is experienced on this side is multiple times the force that I am applying on this side. That's why it's called a lever. It leverages, provides you leverage. Okay, so you apply a small force and you lead to, and which leads to a big force, the load arm. That's why you see the load arm that has the, it will have the smaller length. Load arm will have the smaller length and it experiences the bigger force. The effort arm will have a bigger length. You will apply a bigger movement, smaller force. Okay, so you apply a bigger movement, and the ratio of this to the other is the mechanical advantage. You're gaining an advantage, you're applying a smaller force, but over a bigger distance, and therefore you cause a small movement. Now, center of gravity is the point on the body where the torque due to gravity or gravitational torque is equal to zero. Okay, so now center of gravity can be found by hanging the object from three different points. So now we have a different problem. We have, the point. We have an illustration of this. Okay, so now there are two fulcrum K1 and K2. And then there is a two weights in between. One is the weight of the body, which is G, and there is one boy sitting in the middle at P. And then you have two forces, R1 and R2, right? To keep this uh, without moving, right? You already know that W1 plus the weight of the lever equals R1 plus R2, but you have two forces, two R1 and R2 both are unknowns, right? So now you have one equation which comes from force equation, right? R1 plus R2 equals W1 plus W. So that is the force equation, right? So the two normal forces R1 and R2 have to balance out W1 plus W. But in addition, if you take moments about one of the points, okay, now let's look at which point he is taking moments. He's taking moments about this point. Okay, so if he takes moments about this point, R1 is the force here times K1G, right? So R1 times K1G, R cross F, right, will be into the plane. So he writes that as negative. Okay? So minus R1 times K1G, right? So then minus W1 times PG. Oh, see that force is upwards, right? So this force is downward. So it comes out, right? So plus W1 times PG, right? And plus R2 times K2G equals 0. So he's taking moments about this point G, right? So when he evaluates each of these, this force itself, what is it going to be? This force itself is going through that point. So it's R is 0. Okay, so only W is there. So 0 times W, 0 times 4G. So that will cancel, become 0. So now when he takes moments, he will end up with a second equation involving R1 and R2. And therefore, he ends up with one equation, R1 plus R2 equals 10G, R1 minus R2 equals 1.2 G. And the second equation comes from taking moments. So you have, in addition to your standard force equations, you also have a vector equation which comes from moments. These kind of lever problems and these kind of ladder problems, they all have this particular involvement. So this is a ladder problem. Okay, so in the ladder problem, there is a rough surface on the ground and a smooth surface against which the ladder leans. Okay, so now you have two normal reactions and you have also friction. Friction on a rough surface and it's stationary. So that also is an unknown. So you have three unknowns. Okay. So you need three equations. Two equations come from your fx equals 0 and fy equals 0. But you need a third equation, and that comes from the torque equation, sigma tau I equals 0, and you can take torque about typically about the point B or the point A. Most often people will take it about the point B because it's much easier than taking it about point A, because if you take it about the point B, there are many more forces acting about the point B than about the point A. You can also take it about the point C. You will just, it is just to reduce the number of unknowns that you take moments about the point B. See, net torque about the point B. Why did he choose B? You can take moments about any point. Actually, he chose B because there are many more forces acting about the point B, and all their torques will become zero. So he ends up with just he will immediately be able to calculate N2, okay, because there are only two forces, 1 and 2. Okay, so evaluating this, look at this question in very, very great detail. The ladder problem will teach you a lot, just as this problem will teach you a lot about adding a third equation from moments. Okay, and you will have to learn how to do this. Okay, now block placed in an inclined plane, he's saying for that as well you can use a torque equation. Okay, so these three are standard problems where moments comes into play. Okay, so I'm going to leave this for now, but these are very, very critical things to understand, particularly because we want students to be able to solve these problems when they show up in the exam, and we want you to understand how these things are applied in the context of particularly for the JE students. Needs to also may get some questions, but you must know, understand it from a conceptual level, because they don't have enough time for each question to for you to do a big solving, but then they will still ask you those questions that try to see if you understand how torque works, how these things work. Okay, so so you must from a conceptual level understand whether you're taking NEET or JEE. So now I'm going to move on to what is moment of inertia, and questions relating to that. Okay, so now what is this moment of inertia? Okay, now we discussed angular momentum. Okay, angular momentum is related directly to the moment of inertia. Okay, angular momentum is just I. Moment of inertia is I, usually represented by the letter I. Angular momentum is I times the angular velocity. Moment of inertia, think of it as a scalar. Okay. Now I times the angular velocity is the angular momentum. Angular momentum is the same direction as omega. Omega is the angular velocity. Okay, so momentum of inertia, right? And therefore, and there are first you must understand the definition of moment of inertia. Then you have to understand the properties associated with moment of inertia. Now, this is a little bit involved topic, so I'll get into it and then I will stop so that you can then learn a little more by solving problems. As I always mention, you have to learn to do these problems first by looking at solved problems in, say, a book like H.C. Verma, or by looking at it in the internet. Also, you can go and look at how moment of inertia problems are solved. Okay, so to understand moment of inertia, right? One way to do that is to look at it when you have a rotating body. You can think of every particle in that rotating body. So the total kinetic energy of the rotating body is the kinetic energy of every particle in that rotating body, right? And every particle in that rotating body has a half mv square. Now, if you had a rotating body, what will be its half mv square? Its half mv square is just the sum of all the half mv squares of all the little bodies in that total body, right? Now, for each of those rotating bodies, the v will equal r times omega. Let's say it's rotating about a particular axis, right? And has omega about that axis. So v equals r times omega. Therefore, you have sigma mi omega ri square. So now if you take that omega outside, the MIRI square, right? The summation of all these MIRI squares, right? This term is I. What is I? Moment of inertia. Sigma MIRI square is the moment of inertia. Okay, so now at a distance r, there is a small particle of mass mi. Therefore, sigma mi ri square will give you the I, or it is gives you the r square dm. Therefore, this sigma will become a cumulation, right? Any sigma is actually a integral, will become a integral. So the mi will become dm, and the ri will remain as r. So you'll have r square dm. So the um, I equals sigma mi ri square, and therefore that will become integral r square dm. Therefore, we say that this is usually denoted as I. Sigma mi ri square is defined as the moment of inertia of the rigid body, not that fixed axis. Therefore, that is called I, and I represents the moment of inertia. All right, so now does not depend on the angular velocity of the body, depends on the shape, size, and depends on the shape and the size and the mass. Okay, so heavier, more moment of inertia; bigger, more moment of inertia. Okay, therefore it is the characteristic of rigid body. Okay, so sigma mi ri square, right? So if you have a thin ring, it is just e, all they are at a fixed distance r, thin circular ring. Therefore you have sigma mi r square. The r will come out, and therefore if you have a ring like that and you have axis like that, so all the r's about the is a constant. Therefore sigma mi ri square, the r square will come out, and therefore you just have r square times sigma mi. Sigma mi is capital M, the weight of the ring itself. Very simple for circular ring, right? But then when you do other bodies, let's say you have a disc, right? Then you have to do this. The r's are changing. Some parts will have small r, some parts will have big r, right? So then you have to evaluate it as a sequence of thin rings. Okay, therefore you have to use r square dm, integral r square dm. Okay, therefore you solve for di equals integral r square dm. 2 pi r dr is the times rho is your r square dm. Okay, so that's what you have to learn, right? And how, so you have to separate it out, and you have to do integral r square dm. So now he is doing this, three particles arranged in an equilateral triangle about an axis. So then each of the individual ones you evaluate it about that axis. Moment of inertia is evaluated about an axis. Okay, therefore you have three particles, and then you evaluate that. Now the moment of inertia is not an easy idea, so that's why I'm going to move a little bit of discussion on moment of inertia to the next class. Okay, you must do some problems involving this moment of inertia, and you must learn how they calculate the individual moment of inertia of a sphere, moment of inertia of a circle, moment of inertia of a disk. Okay, and then you have to understand also these theorems around moment of inertia. Okay, perpendicular axis theorem and parallel axis theorem. Only if you learn both these theorems does it become any easier. Okay, now because this is a little bit tricky, I'm going to move it to the next class. But you must understand that a hollow cylinder is just a series of discs, of thin rings, right? Series of rings, and for the ring you evaluate, right? Mr square. So the cylinder also will become mr square, right? So each of the hollow disk is, now if you had individual disks, right? So hollow cylinder is also mr square, because it's just a series of disks. Now if instead of that you had a uniform disk, right? A uniform circular disk. Let's do uniform circular disk, right? A uniform disk is what? A series of rings. Each of those rings is mr square, right? And what is the m for each of those rings? The let's say this ring is at a distance r, right? What is its mass, right? Its mass is 2 pi r dr. What is 2 pi r? 2 pi r is the circumference times the thickness. Thickness is dr, right? 2 pi r is the circle, is the length of that ring. 2 pi r times dr times rho. Rho is the mass per unit area. Okay, so because it's a uniform circular disk, that's why they use the word uniform, right? So what is if you had something which is of the area 2 pi r dr, what will be its total mass? It will be 2 pi r dr times rho. What is rho? Rho is the total mass divided by the total area. What is the total area? Pi r square, right? So m equals pi r, capital R square, rho, right? So m divided by pi r square equals rho, right? So 2 pi r dr times rho times r square. Well, what is that times r square? Sigma m r square, right? So 2 pi r dr r square. Then you will go from you'll do the integral from 0 to r. So you write di equals something, then integral di equals I. So then when you do that integral, you end up with mr square by 2. Okay, so that is the uniform circular disk. So once you learn uniform circular disk about an axis perpendicular to the plane of the disk, so if you have a disk like this about that axis, and let's say it's spinning like this, what is its angular momentum, right? It's spinning with the omega, right? So its angular momentum is mr square by 2 times that omega. Okay, now it is different from when you have a rod that will have a different moment of inertia. It will have its own I omega. Okay, it may have a different mass, or it may have the same mass, but it will have a different angular momentum. I times omega is the angular momentum. So with that, I'm going to stop and I'll take up the discussion at exactly this point, because I don't want to overpack the discussion here, because I want to spend 1 more hour discussing this and then do some problems next class. But there are a lot of types of problems that you will get in rotation. There's the standard rotation problems, angular velocity, period, etc., related problems. And then you have alpha cross, the tangential versus radial related problems. Then you have the problems involving the earth, the moon, and the sun. And then you have the problems involving the torque. Then you have the problems involving moment of inertia. Now, just as I omega is L equals I omega, similarly tau equals I alpha. Okay, just as F equals ma, tau equals I alpha. Okay, so remember that as well, right? dl by dt, right? dl by dt equals tau. Therefore d, because L is I omega, d, you take the I out, you have I times d omega by dt. D omega by dt is alpha. Okay, so with that, I'm going to stop, and therefore all these concepts are related. I want you to listen to all the details that I discussed. I don't want to cover everything all at once, but then I'm going to stop here. Okay, then we will continue the discussion in the next class. All right, so with that, I'm going to stop, and then we will continue discussing this